Hi, Jim Berthold here from OLI Systems. Today we're starting a series of videos on how to do some light data regression for entering a new component into our databases which don't previously exist. The species of interest for the series of videos will be silver phosphate because it doesn't currently exist. However, to enter data, we have to get started by using our new OLI Databook program, which you can see before you. So we're going to start with a very simple tutorial about what's available in the database. And we'll start off by opening up an existing system database. And to do that, we're going to go over here to the File menu. Now we could search for it, but if we use the little tiny drop-down button next to it, we can go ahead and open up a system databank. This should take us directly to where the databases are stored with the software. This database folder is common to all of the OLI products currently installed on your computer. For this particular example, we're going to go to the MSC Pub database. This is the master database for the mixed solvent electrolyte thermodynamic framework. So we're going to just go ahead and click open. It will take a second or two, and it gives you a little tree view here with species, interactions, material codes, redox, absorption, and literature. For those of you who've used the old blue screens for the OLI Databook program, we have maintained the similar structure. For this case here, we're going to go look over here onto the panel here. It is a MSC database. You can't change it once it's created. The name of the database is MSC Pub. This is what you will see in some of your screens. But the more common name is the MSC H3O Ion, which you'll see in places like OLI Studio when you're selecting databases or OLI Flowsheet. In addition to that, the creators of this database have tagged it with a version number. This is version 11 software, and it is revision 1 of the software. So it's sometimes nice to know what version we're using. Later versions will have incremented numbers. So we're going to start off by looking at species first. So we'll go ahead and start looking at a species. We're going to pick a very common species. But first, let's talk about this little panel here. It is scrollable, and we have 3,366 species currently in the MSC Pub database. You can use this tool to search for species, although the OLI Data Locator tool described in other videos is far more efficient at searching for a component than this tool. But we do know that carbon dioxide, CO2, is present. So we'll go ahead and type in CO2 in the search box, and we'll just click on the CO2 line here. This displays some information right here, and some things are important and some things are useful. So let's talk about the important things first. Well, first off, the creator, that would be the person who's using the software. At the time I created it, it is me. It was last created in January 8th of 1992. So this component has been in our database for a very long time. The IUPAC name is useful but not necessary. The component number is there for other programs such as Unisim Design, which requires an indexing of values. The formulas, both the empirical and chemical formulas, are the same in this case. The Chem Abstract service number is here, and the first value that's absolutely mandatory is the molecular weight here, and this is grams per mole. The other things that are interesting here is the ASID and the ASNM. These are variables necessary for the Aspen Plus program, for us to automatically link them to components in Aspen Plus. Other things that are important or useful on this page are the synonyms for it. But other things that are absolutely mandatory are the material codes. These are the internal components that make up this molecule. And we have a carbon in a +4 oxidation state and oxygen in a -2 oxidation state. And there are arbitrary numbers assigned to them. In this case, carbon +4 is code 25. And code 21 is oxygen. They are completely arbitrary. They're more historical in nature than anything else. The molecular weights are stored internally, and you have to tell the program when we do an actual edit of this later on in this course, how many carbon 4s you have and how many oxygen minus 2s you have. These will automatically update this field so everything has a common basis for molecular weights. Now, carbon dioxide has two phases stored. The first is the vapor phase, and the critical parameters and eccentric factors are entered here. Okay. You can change the units. For example, if you don't like critical pressure in pascals, you can bring it into a variable that a lot of us use, our bar, and you can see it changed automatically. There are Gibbs free energies of formation, enthalpy, entropy, and heat capacity, and so forth. We consider those proprietary. They're masked in this view, but when we do our data entry, we'll be able to enter them as needed. There are other variables, vapor pressure coefficients and heat capacity coefficients. These are also considered proprietary, so they're masked and you can't view them here. The aqueous phase, actually, let's go back to the vapor phase. The last thing that's important on this thing is the VLE equation, and we always write it in terms of vapor to our aqueous phase. That's the OLI syntax. Under the aqueous record, we again have the reference state thermodynamics present here. There is a variable called racket Z. This is a version of compressibility. This allows us to do some non-aqueous phase thermodynamics. These are some parameters that we have in here for our MSE equation of state. Again, the most important thing here is the aqueous phase reaction, if any, and we write it in terms of water. Carbon dioxide plus water gives us hydronium ion plus bicarbonate ion. There are also other parameters listed here. Also, again, these are all masked because we consider them proprietary, and you can't see them nor change them. But in this short course, we will, in fact, change them. I want to look at the different species here just to show you that we have solids. Sodium chloride we'll put in. Okay, and we'll go ahead and use it. Sodium chloride is similar with the information we have here. Now, sodium chloride is a little different in terms of it doesn't have an Aspen ID record here. It shows up in the solid phase. Here's the Aspen record there, because solids are treated differently in Aspen plus than OLI. It also has material codes and synonyms, but the material codes are absolutely important. They must be done correctly. Other things are a little different here. The OLI tag name is NaCl. There's a mineral name is halite. This shows up in places in the code, so you can tell different crystal forms with the same stoichiometry. The empirical formula and the chemical formula are different. The empirical formula is alphabetical. It's actually C, H, and O. Then everything is alphabetical. And the chemical formula is more what we would see if we were writing it down ourselves. For the solid phase, it's just slightly differently. Here again, we mentioned that the solid phase has a different Aspen ID if you're using Aspen Plus, and the equation here. So we write our solids either as PPTs or hydrates. I'll show you a hydrate in just a second, dissociating into their ions. Okay, again, the dots here indicate the values are masked. Last one I'll show you here will be sodium carbonate. Now, I just typed in a little bit of sodium carbonate, and you can see that we have hydrates and double salts present. I'm just going to pick the decahydrate as an example. Again, the general information tells us how it's going to look to us, molecular weight being the most important. Here are the actual stoichiometries and MAC codes that we need, and we'll show you that as we're creating the soft species. This is the only synonym we have present, and here is the solid record information. Aspen ID is slightly different. It's instead of having a dot value, they're using the word W to indicate the number of waters associated with the solid. And this is how OLI writes the dissociation. Sodium carbonate decahydrate, it gives us 2 sodium, 1 carbonate, and 10 waters, and that's how OLI writes their equation. Okay, so that's pretty much the only thing to see here for the species. We do allow interactions. Okay, so if you wanted to see all of the interactions involving hydrogen sulfide, we could put that in there. It's not a good search in that it'll also pick up sulfate. Okay, so we can't limit it. But we have things that, so here's a decane hydrogen sulfide interaction. If we picked it, it shows up in a different tree. And we can see that we have parameters in there for the MSC parameters. Again, we are masking it because we consider proprietary. Under material codes, we list all of them that we're using in the software, but you can search, for example, if you're searching for hydrogen, it'll show you everything that's got those. It's not a very good search there for that because it's very quick. But if you wanted all the MGs, let's pick something that's like CL. Chlorines have different oxidation states. There's a -1, +1, all the way up to +7, and they have different codes themselves. If you look over here on the codes, we're looking at chlorine +7. This is the internal number. This is what you're going to see in the program. This is the actual charge and the molecular weight. And this odd value here is a liquid. This is the theoretical liquid volume of this component at reference state conditions. Okay, and it's really arbitrary. It's fake to some degree. It's there to fill a hole in other software packages other than OLI, so we don't throw error codes in those software packages. We do have literature, but we're not actually using the literature values as much since our literature sources are so varied, but we keep them there historically. All right, that was a long time to explain what's going on inside our software for this. To finish it up, we do have user data banks, which I have here. Some of these came directly to us from customers. Some of us we created ourselves. Okay, and I can't show you all of them because some of them are proprietary, but I created Krypton. So I'll just go ahead and create Krypton here to show you that we can do this. So Krypton is an empty database, and I could actually put in the OLI name, KR. Okay. And I could add more things to it. The material code here, I have no idea what Krypton is. Typing it in, I might be able to find a Krypton in here someplace. Lord only knows where it is. So I would go back to MSC Pub, go into the material codes, and see if I can find Krypton. And there it is. It's code 564. If I come back to the Krypton database, since we're already keeping it, I already had it in here. It must have just been slow. Okay, but I could enter that stuff. Aqueous values I've entered in myself. Here I have equation of state coefficients for them. We'll teach you all of that in the course. Here's the vapor components. These fields are all editable, so you can change them as need be. Okay. So it's just to show you that we can, in fact, edit material here. The thing about Krypton here is it is an MSC database. I can't change that, but I can change its name. The last thing is if you are creating your own database, the first 3 characters, in the case you see here, KRY, they must be unique within the entire list of species within the folder. So I couldn't create a Krypton 1 then a Krypton 2 database for whatever reason. They have to be substantially different this value here. The full name could be the same though. When we're done, we'll just hit the Save button, and we're ready to exit the program and move on. Thank you very much. Thanks for watching.